Hey there, everybody. Today we're going to talk about uniform circular motion, a very well described concept. Uniform. That means our speed is going to be the same as we move in a circle. We're going to move in a circle at a uniform speed. And we're going to move in a circle that doesn't change its radius, so that's going to remain the same as well. So we want to understand this kind of motion. We're going to talk about, we're going to review acceleration, what it really means, and discuss the fact that you can feel acceleration. And then we're going to talk about the kind of acceleration that makes you move in a circle. We're going to call that centripetal acceleration. And we'll show that the magnitude of centripetal acceleration, which we're going to call a sub c, will be equal to our speed squared divided by the radius. And then finally, we'll talk about the period of rotation. That's the time it takes to go around in a circle one time. The time to go around one time is called the period. And we'll show that it's 2 pi r, r being the radius, divided by our speed. And this is the speed, really. I mean, it's not our, it's the magnitude of our velocity, our instantaneous velocity as we go around that circle. All right, so let's get started. First, let's talk about acceleration. We've defined acceleration in general as being acceleration is, well, instantaneous. We use this limiting thing, but the key idea here is it's a change in velocity over a change in time. Key idea, this is an acceleration, and velocity is, this acceleration is a vector, and this velocity is also a vector. And you can change two things about a vector. You can change its magnitude, or you can change its direction. And the change in direction is what we're going to see here. Now let's talk about acceleration that you can feel. Suppose you're, here's your little car, and you're sitting in your car, and you choose to, let's say you're at a stoplight. Here's the road. What do you feel as you accelerate forward? Right? You can feel an acceleration. Right? Now the irony is that when you accelerate forward, what do you feel? Well, when I accelerate forward, I feel like I'm getting pushed backwards, don't I? I mean, yeah, I do. I feel like I'm getting pushed backwards. Now, suppose you accelerate forward, and now you're going, high speed. So here you are in your jalopy, and you're going a high speed, and if there's no acceleration at all, you're not slowing down or speeding up, you really don't feel anything, do you? In fact, if your car is really smooth, there's really no way to tell how fast you're going except by looking at the outside world. I mean, even if my eyes were closed, I can tell that I'm accelerating forward because I feel myself getting pushed back. But if I'm moving with constant velocity, I don't really feel, I feel that maybe the vibration of the road and wind noise and so on. But if I close my eyes, there's really nothing I can do to tell how fast I'm going. That turns out to be a really profound idea if you ever study special relativity. But then, I don't know, you see a small child playing on the road. Here's our little small child. And you decide, well, I guess for this one I'll stop. So you hit the brakes, right? So here you are in your car, and you're moving forward pretty fast, but you hit the brakes. So that means that even though your velocity vector is forward, your acceleration vector is backwards. And that's when you slow down. When your acceleration vector is in the opposite direction of your velocity vector, you slow down. And what do you feel when you're in that car when you slow down? I mean, what do you slam on your brakes, or whoever's driving the car slams on your brakes? What do you feel? You feel like you're being shoved forward, don't you? You feel like you're being thrown forward in the car. Now that's because you have inertia. You have mass and you have inertia, and a force needs to be applied to you to change your velocity to give you that acceleration. And we're going to study that in the next unit. But for right now, it's good enough to say, hey, when I'm accelerating this way, I feel as if I'm getting thrown forward in the car. And hopefully we stop in time. I'll leave that to you. Now, there is another kind of situation when you're in a car where you feel like you're getting thrown in a particular direction, but you're not speeding up and you're not slowing down. Can you think of an example of that? Well, let's say you're driving down the road and you're a new driver and it's late at night and there's this big empty parking lot. Now, I am not advocating that you do this, but I have seen people, I've had friends that do this. So anyway, imagine a big parking lot. We're going to look down on this parking lot. And somebody in a car decides they're going to put down a donut. And so they try to drive in a circle. So imagine you're driving in a circle. You go, so here's your car. We're looking down on this. Okay, and the car is moving. There's your velocity vector at that instant in time, but you're going to be moving in a circle. Now, what do you feel when you drive in a circle? What do you feel? Well, now think about it. This person is making a left turn, aren't they? A constant left turn as they go around this circle. What do you feel? Well, when I turn left, don't I feel as if the universe is trying to throw me out the car? You feel like you're getting pushed to the right, but actually what's happening is you feel an acceleration that's actually directed to the left. If you're turning left, the acceleration is to the left. So this is my acceleration vector. And this acceleration vector, you feel acceleration. That's the point here. If you accelerate forward, you feel like you're getting thrown back. When you accelerate backwards, or you slow down, you feel like you're getting thrown forward. When you move in a circle, you feel as if you're getting thrown to the right, but really what's happening is you're accelerating to the left. And you might ask yourself, hey, wait a minute, how can I have an acceleration if now let's say you're right here, and and a few seconds later you drive around here, and now your velocity vector is like this. And let's say, hey, the magnitude of my velocity hasn't changed. That is, I'm driving around this circle with a constant speed. But something did change about my velocity when I went from here to here. It's not the magnitude that changed. It is the direction that changed, right? And that's a change in your velocity. And to change your velocity over time requires an acceleration vector. Well, if you're over here and your velocity vector is the same, you're going to feel an acceleration vector. If you're right here and your velocity vector looks like that, in order to turn, you need an acceleration vector. So what we have here is an acceleration that's perpendicular to my velocity vector at all times. Think about it. If I had an acceleration vector that wasn't perpendicular to my velocity vector, let's say I had a velocity vector that was up like this a little bit. Well, that means that a component of that velocity vector would be in the same direction as a component of that acceleration vector would be in the same direction as my velocity vector, and I would speed up. If it was down like this, I would slow down, but I'm not. I'm moving with constant velocity in a circle, and I need an acceleration to do that. Because acceleration is a change in velocity over a change in time. Right? This is average acceleration. But if I take the limit as delta t goes to 0, that becomes dv dt. This is a rate of change of velocity. And I'm not changing my speed, I am changing the direction of my velocity, and that's the key idea here. Okay, so here's what you get. You get uniform circular motion if you don't change your speed, but you do change your direction at a constant rate, and you'll go in a circle like that. Now, doesn't it make sense that the faster you go, the more you feel this outward kind of acceleration that really isn't there? It's really an inward acceleration. Doesn't it make sense that the faster you go, the greater that acceleration? That's true. And have you ever gone around a hairpin turn or a really sharp turn? If you make a really sharp turn, don't you need a lot of acceleration to do that? Whereas if you want to make a nice easy turn, you make a nice big radius going around. Yeah. So the smaller the radius, the greater the acceleration. That's why they want your speed limit to be really low when you go around a really sharp turn. Well, what we want to do is figure out, well, what is the magnitude of this acceleration? We know what the direction is. It's perpendicular to the velocity vector. But what is its magnitude? And so what we're going to do, let me redraw a circle here. We're going to move in a circle. So here's my velocity vector. Okay. And I'm going to call this my initial velocity. And then at a short time later, I'm going to be moving like this, right? And this is going to be my final velocity. Okay. Now, I know that if I take my initial velocity vector, and let's just transplant it over here, my initial velocity vector plus my change in velocity will be equal to my final velocity vector. Now, my final velocity vector is going to be this length and this length. I'm trying to draw them the same. So they're the same. But what you have here is, this is my delta v vector. I have a change in velocity vector. And that change in velocity vector looks like this. Remember, delta v, let's think about a vector equation. Whoops. V final minus v initial, right, is delta v. But I can rearrange this vector equation, to say that v final is equal to v initial plus delta v, right? And so that's what I've drawn here. I've got v initial plus delta v equals v final. And it makes a little triangle. Now, what kind of triangle is this? Look, it's got these two sides are the same length. That is, this velocity and this velocity have the same magnitude. They're just in a different direction. So this is an isosceles triangle. Now let's look back on my circle here. Here's the center of my circle. And here's let's say my axis is right here, my origin. We'll call this my origin. This is R initial. That's my initial position. Here's R final. Now because I'm moving in a circle, R final and R initial have the same magnitude, because the radius of the circle is the same. But we know that R initial plus delta R, here's delta R in here, R initial plus delta R is equal to R final, right? So this makes a triangle, just like this is a triangle. Now this is a velocity vector triangle, and this is a position vector triangle. But here's the deal. If I rotate R a certain angle, I have rotated the velocity by the same amount of angle. So if this is theta, if I rotated this, well, think about this. Let my finger be the velocity vector, right? If I rotate this by theta, this, well, I'll use this pencil here instead. You see that they kind of go like this? The velocity vector rotates the same amount of angle as the position vector, or radius vector here. So if this is theta here, this is theta here. Well, what does that mean is true about these two triangles? They're both isosceles, and they both have the same angle here. So these two triangles, what do you call two triangles that are like that? They have the same angles, all these angles are the same. They're similar. And if they're similar, then they're proportional. And therefore I can say this. I can say, let's see, what is it? Delta V. And let's just talk about the magnitude here. Delta V over V. And I'm just going to call this V, our speed, because our speed doesn't change. Delta V over V is equal to delta R over R. Right? So this is our radius. The magnitude of our position vector is just the radius of the circle. And this is delta R here, which is delta V. Okay, over V. See this? Any questions here? Okay. Yeah, if you're watching online, you can't ask me a question, but you can always ask me on Facebook or something. But if you're in class, ask me if you don't get this. Okay, now we've got this proportion here. So now I can do anything I want to it, and what I'm going to do is this. I'm going to divide both sides by the time it took to go from here up to here. The time interval, to change in time from here up to here. And I can do that. Well, let me rearrange this now. This becomes 1 over V times delta V over delta T. And then this is going to be delta R over delta T times 1 over R. Okay, I'm just kind of rearranging this a little bit. Then what I'm going to do is a little trick. I'm going to take this whole expression and I'm going to take the limit and I'm going to let delta T go to 0. Okay? Now what do you get when you apply the limit to this? Well, 1 over V. V is a constant. Right? This is just the speed. The speed is a constant. So it's just 1 over V. But what is delta V over delta T? When you take the limit as delta T goes to 0. Well, that's acceleration. And what is delta R over delta T as you let delta T go to 0? Well, that's my velocity. And what I'm going to do now is just solve this for velocity. I'm going to multiply both sides. I'm going to solve for the acceleration. And I'm just going to multiply, that's right, I'm just going to multiply both sides by V. So multiply this side by V, and I get the expression that I wanted to derive. The magnitude of my acceleration is equal to V squared over R. Now this acceleration, this is the expression for the acceleration that changes the direction of my velocity vector as I move around in a circle. It's not changing my speed. That's staying constant. It's changing my direction, and it's changing it at a constant rate if I'm moving in a circle. Now, what is the direction of this? Well, it seeks the center, right? The direction of my acceleration is always towards the center of my circle. So it is a center-seeking acceleration. And we have a name for center-seeking accelerations. We call them centripetal acceleration. Well, centripetal acceleration is a sub c. It's equal to v squared over r. Okay? And that's what we tried to show. Now, and this is a basic equation. We're going to use this a lot. And that C stands for centripetal, which means towards the center. And this, again, is our speed, or our velocity vector squared. We'll talk more about that later, divided by the radius of our circle. Okay, one last thing to talk about. If I'm moving in a circle like this, okay, at a constant speed, right? Well, speed, we also said, was the distance traveled divided by the time it took to go that distance. Well, let's define a particular time. And we're going to say the time it takes to go around a circle one time We're going to call that the period. The period, we use a capital T to represent period, and it's the time to go in one circle, or one time around the circle, to go in one circle. Okay, well, if I go around the circle once, what distance did I travel? Well, I traveled the circumference of that circle. So I can say that my speed is equal to the distance, 2 pi r, over the time, which is my period. And then I can just solve for the period, and the period is equal to 2 pi r, the distance around, divided by my speed. Okay. Now actually, in the book, this is the basic equation, but I like thinking of it as this. This is really easy to remember. The speed we go around is the distance divided by the time. The distance around the circle once divided by the time around the circle once, which we call the period. Okay, so let's review real quick. We said that acceleration, we can feel it. We can feel it, but what's odd about it is that we feel the opposite of it. If I'm accelerating forward, I feel like I'm thrown back. If I'm decelerating, if I'm coming to a stop, I feel like I'm being thrown forward. And the same is true for centripetal accelerations. The acceleration that makes you go around a circle, if you're going around this way, you feel like you're being pushed to the right when actually you're being pushed to the left. And you feel that acceleration. And then we derived an expression for what that centripetal, that center-seeking acceleration is. We used a little trick with similar triangles. We set the limit as delta t goes to 0, and we came up with the centripetal acceleration is equal to v squared, our speed squared really, over r. And then we used that to, we expressed that speed in terms of the period. The speed is also 2 pi r over the period. And, that's good enough. Here's our basic equations here and here, and you now know enough to do all the questions and problems regarding centripetal acceleration.